Hey there, everyone. This is our Eddy current tachometer project. We are Group 8. My name is Matthew Sanchez.
My name is Jana Shah.
And I'm Mia Travis.
And we're going to take you guys through our presentation for our Eddy current tachometer. So starting off with a bit of historical background, we wanted to talk about who invented the tachometer and what led to it being used in modern day applications. So a tachometer is an instrument that measures the rotational speed of a shaft or a disc within a motor or other machine. That's why it's used a lot on cars these days, for example. The world's first tachometer has been credited to German engineer Dietrich Ohlhorn in the year 1817. Nowadays, the gauge will display the revolutions per minute, or RPM, on a calibrated analog dial. That's why you see it being used in lots of vehicles. Think of an automobile, for example. But its first use was actually on a vehicle in 1840, and that particular vehicle was a locomotive train. So, project introduction. What was our task? Why did we choose eddy current? And let's give a quick overview. So, in terms of the task, we needed to design, build, and calibrate an eddy current tachometer that displays the rotational speed of a shaft, both mechanically with a dial pointer and digitally with an LCD display. So, why did we choose eddy current? We chose eddy current because we figured it was durable and there was many past examples of successful implementation. So, we decided to go off of that. We'd have a lot of stuff to work off of. A quick overview of the project components and the goal for that. We wanted to have a controllable motor shaft assembly, so we'd be able to vary the speeds at various RPM. We wanted a conductive disc made out of aluminum. We wanted fixed magnets to induce an eddy current, and to fix those magnets, we 3D printed a holder, which we'll show later on. We wanted to spring load the dial so that the spring resistance could correlate to a certain RPM. We wanted the LCD digital readout, and we wanted to calibrate the setup after it was all done with the laser tachometer. So a little bit about project theory. I'm going to go over electromagnetic induction. So as a conductor moves through a magnetic field, the flux passing through changes with time, and the change in flux is caused by changing is the change in flux is caused by the changing magnetic field, which applies force to the free electrons in the conductor. Those electrons are going to move around and produce an induced current inside the conductor. And the process of generating an electric current by a changing magnetic field is called electromagnetic induction. As you'll see throughout the project, there's no physical contact between the conductor and the magnet. Rather, the magnetic lines of force will pass through the air or medium if the coil is wrapped around a metallic core. And going over the self-inductance principle. So when a solid piece is brought near a moving or rotational magnetic field, voltage is induced and current flows. This is what we call the eddy current. So the metallic piece is going to be the solid conductor in the setup, and the eddy current is going to produce a directionless current, and that current is going to produce its own magnetic field around the solid conductor.
So we will go more in depth in the project theory. Here, the shaft is connected to the cup and spring. The cup rotates with the magnet and stops when the force of the magnetic field becomes equal to the opposing spring. This can be shown in the picture on the right side. The spring force is calculated by using torsional stiffness and multiplied by the angle of turn. As the shaft speed increases, more voltage is induced and more current flows, which induces more magnetic field, and the force increases. As to the deflections of the spring and the dial, this deflection of the spring can measure the speed of the shaft, which is shown on the dial. Next, we will go over the bill of materials. We used an Arduino starter kit, which comes with a motor, which we used in our project. We also ordered the 6 mm stainless steel Amazon, and also the leaf bearings, which are mounted on the 3D printed brackets. The 3D printed brackets for the motor, shaft, and magnet holder were printed by our friends. The conductive disc was made of aluminum foil. The dial material was from cardboard, and we used neodymium magnets for inducing the magnetic field. And we used wooden base for stability and two couplers on each side for holding the shaft. Total comes out to about $83. The setup and implementation. So all the parts were mounted on a wooden board for stability. We used power source from a 12-volt battery, which was attached to the motor. The motor was on a 3D printed bracket, which was made of PLA and resin. The shaft was a 6 mm diameter shaft, and it is connected to the motor by a 2 mm to 6 mm coupler. The drag cup was made of aluminum foil, folded about 5 to 6 times, and the magnetic field was induced by 6 neodymium magnets, about 0.7 inch in diameter each. The motor control was done by Arduino Uno R3 for, for controlling the motor via a throttle. Here we can see the whole setup in action. The motor is mounted on a 3D printed bracket, along with the shaft going through the resin bracket. And at the end, on the other side, the aluminum foil is also held up by 3D printed bracket, and the motor is connected to the Arduino.
Next, we have calibration and testing. So although we couldn't get variable speeds on demo day, this is how we would have calibrated and tested our tachometer. So for the dial system, we would point a tachometer at a reflective strip or marker on the rotating shaft and record the RPM. We would also take note of the pointer's angular deflection at various motor speeds so we can get an accurate RPM reading. We would plot the pointer angle versus the RPM from the tachometer, and we would fit a line, linear or polynomial tread line. And then we would mark the correct RPM values on the digital face for direct readout. And then for a digital reading, we would run the system at various speeds and ensure that the Arduino is counting pulses and displaying RPM. Simultaneously, we would use the handheld tachometer to make sure that this is correct. If the Arduino RPM readings match the handheld tachometer values, then the calibration is confirmed. If there was a consistent error, we would adjust the pulses per RPM per revolution, the PPR, a variable in code, and apply a correction factor in the RPM calculation. We would repeat across the RPM range. Some improvements. What we could have done better, for our power source, we use a 12-volt, 1.3 amp battery, which is an oversized battery for the purpose of this project, which ended up heating the motor very quickly. For the dial system, we originally got torsional springs that weren't correct, and due to lack of time, we're not able to get the dial system correct. So next steps and future improvements. For our power source, we would use a better suitable battery with the appropriate current rating. And then for the dial system, we'd order torsional springs with the appropriate size rating and spring constant in order to have a dial system working correctly after calibration. And then some conclusions, some more next steps and future improvements. We would have done a better Gantt chart and complete the task by the deadlines. We underestimated the scope of the work of the project, so we weren't able to get the correct things done in time, and we didn't have the correct spring. We would perform more research on the parts needed and size them correctly. So one of the main things was that the mounters for the motor and for the rotational shaft were slightly off, so we had to use bits of cardboard to make them more level. So more stability on this would be needed for the mounting. And then we would use screws rather than gluing everything down together. And then some conclusions and takeaways. We understood the concept of eddy current and magnetic field generation. And then the eddy current tachometers convert rotational speed motion into mechanical deflection and can give a digital RPM reading, which is useful for many applications like set your car. Thank you.